Hello everyone, my name is Abdulkarim Khormi, a PhD student in the Department of Computer Science at Florida State University. Today I'm presenting a study on the accuracy of OCR engines for source code transcription from programming screencasts. I'm the author and my co-authors are Mohammad Alahmadi and Professor Sonia Haiduc. So let's get started. According to a recent research, programmers spend 20 to 30% of their time online looking for information to support their daily tasks. And one popular source of information is programming screencasts. Moreover, YouTube alone hosts vast amount of videos that cover a large variety of programming topics. However, available programming screencasts lack the support for code reuse, since very few programming screencast creators that provide the source code alongside the video. And also, online platforms like YouTube do not support automatic code transcription. So researchers have recently recognized this problem and proposed novel techniques to automatically detect, locate, and extract source code from programming screencasts. And we noticed that all recent research use an optical character recognition engine or OCR engine to extract the text from image. So to ensure the most accurate extraction of source code from programming screencasts, we believe it's important to carefully choose the OCR engine that performs the best for code extraction. However, there is no empirical evaluation currently exists on the accuracy of OCR engines for code extraction, and previous work on code extraction used Tesseract, with no evidence that Tesseract is the best option for code extraction. So we believe that choosing a suboptimal OCR engines can lead to noise that is not easy to correct. To this end, there is a need for an empirical evaluation that study the accuracy of different OCR engines for extracting source code from images. So for this study, we evaluated 6 well-known OCR engines. So the first is Tesseract, an open source OCR supported by Google. And the second one is GOCR, which developed by Jörg Schellenberg. And also we have Cuneiform from Cognitive Technologies, and OCR 80, which is developed by Anthony Diaz. And also we have Google Drive OCR from Google, and this is only the engine that required internet connection. And finally AB FineReader, which is from AB and which is a commercial tool. In order to get the accuracy of an OCR engine, we need to compare the ground truth, which consists of the image of source code and the actual text of the source code of the image, with the output of the OCR engines for the same image. So to evaluate the OCR engines, we collected 2 datasets. First, the YouTube Screencast dataset, the second, Screenshots dataset. For YouTube Screencast dataset, we first collect the image and then we transcript the source code from the image. For screenshot dataset, we did the opposite. We first collected the source code and then we screenshot the ID of the source code to produce the image. It's possible to create more than one image by using different settings, for example, using different font type and different font size. So let's talk in details about YouTube Screencast dataset. For the first part of the ground truth, the code image, we turn it to YouTube, where vast amount of programming screencasts are hosted, and which is common among researchers. So to ensure the variety of the dataset consists of 3 programming languages: Java, C# and Python. We collected 100 screencasts for each programming language, in total 300 videos. Finally, we selected one representative frame from each video and we crop it to the code snippet. For the ground truth source code, we manually transcribe and validate the source code using in-house web-based tool that we developed to simplify the process. And finally, for the extracted source code, we used the 6 OCR engines to extract the source code from the 300 images. We obtained 300 text files for each OCR engine, in total 1800 files for all the OCR engines. For a larger dataset and to study the different factors such as font type and font size on code extraction, we collected the screenshot dataset. First, for the ground truth source code, and to ensure the variety, we collected the top 50 projects in GitHub of the 3 programming languages, Java, C#, and Python. In total, 150 projects. From each project, we selected one source code file, in total 150 files. And to make sure all the code can be displayed in the IDE, we reduced the lines of each file to a maximum of 35 lines. For the code image, we used the 150 source code files, and for each file, we record 25 combinations of 5 font types and 5 font sizes. So in total, we recorded 3,750 images. We chose the font types and font sizes based on the following. We studied the default font settings in Linux and Windows of the top 5 IDEs according to GitHub at the time of the data collection. We found that the IDEs used 3 font types, which are Khormi, Consolos, and the Java Sans Mono, and the range of the font size from 10 to 14. As a result, we included the 3 font types which are monospaced. Monospaced means that the width of the letters is identical. We also added 2 non-monospaced fonts, which are Arial and Times New Roman. Also, we included the default font sizes from 10 to 14 to our study. In order to record all the screenshots with the different settings, we need first to open the source code file in an IDE. Then we need to change the font type and font size 25 times. And finally record the screen for each combination of the font type and font size. It's not easy to do this task manually. For that reason, we develop a tool to automate the process described above by simulating the keyboard input programmatically and recording the screen into an image file. Finally, for the extracted source code, we used the 6 OCR engines on all the screenshots to extract the code. We obtained 3,750 text files for each OCR engine. In total, 22,500 files for all the engines. We evaluate the performance of an OCR engine by comparing the ground truth source code and the extracted source code. We used Levenshtein distance and edit-based metric to calculate the distance between 2 texts. Levenshtein distance counts the required number of insert, substitute, and delete operations to change a text to another. Finally, we normalize the Levenshtein distance to obtain an accuracy score between 0 and 1, with considering the length of the text. The Levenshtein distance counts the extra spaces and lines as regular characters. However, many programming languages ignore them. For that reason, we ignore the leading and trailing spaces and blank lines for most of our study. However, white spaces indicate grouping statement in Python. For that reason, we add an extra study for Python source code with and without the trimming process. Finally, we computed the NLD scores for all the extracted text against the ground truth to answer 6 research questions. The first research question is regarding the accuracy of OCR engines for the video frames. As we can see, these are the result of extracting source code from YouTube Screencast dataset. So we can see here, Google Drive and AB Fine Reader scored the best accuracy with 95 and 93% on average respectively. After that, GeoCR scored 67% on average, then Tesseract with 57% on average. Finally, OCR-AD and Cuneiform performed the worst with 26 and 20% on average respectively. The second research question is regarding the accuracy of the OCR engines on the overall of the screenshots dataset. As we can see here, AB Fine Reader and Google Drive also scored the best accuracy with 96 and 94% on average respectively. After that, GeoCR followed with 78% on average, then Tesseract with 60% on average. Finally, OCR-AD and Cuneiform performed the worst with 32 and 18% on average respectively. For the OCR engines and font types, the font Djavo Sans Mono performed the best among all the other fonts for 4 out of 6 OCR engines. Djavo Sans Mono achieved the highest average accuracy of 71%, followed by Consolas with 67%, and the average accuracy of the other font types, Arial, Courier, Neo, and Time New Romans were 63 and 60 and 54 respectively. For the OCR engines and font sizes, as we expected, the results show that the accuracy increased with the increase of the font size for all the engines. Google Drive and AB Fine Readers were barely impacted by the change of the size, as both of them scored more than 90% for all the font sizes. For the programming languages, here we have the result from the YouTube Screencast dataset. We can see that the OCR engines scored the highest accuracy on Java source code, followed by C# and Python, with an overall accuracy across all OCR engines of 62% for Java and 56% for C# and Python. For the screenshots dataset, the OCR engine scored the highest accuracy overall on Java source code also, and followed by C#, then Python, with an overall accuracy of 74%, 59%, and 55% respectively across all the 6 OCR engines. For the trimming experiment on the Python source code, and by comparing the extracted source code with the trimming step of the white spaces and blank lines, and without the trimming step, the result shows that the trimming step enhanced the accuracy of all the 6 OCR engines by an average of 6.5%. Finally, for the time performance of the OCR engines, we used the time command line during the experiment. The result shows that OCR-AD is the fastest, followed by GeoCR, then Cuneiform. Tesseract, AB Fine Reader, and Google Drive followed them respectively. To conclude, we performed an empirical evaluation on the accuracy and the speed of 6 OCR engines, and we collected and used 2 datasets from 2 different sources. The first is Programming Screencast, and the second is Source Code Screenshots. We showed the impact of the font type and size on the code extraction for the OCR engines. Moreover, we found that AB Fine Reader and Google Drive spend longer time than others to produce the most accurate result for code extraction. Also, OCR-AD, GeoCR, and Cuneiform were the fastest engines for the code extraction. However, OCR-AD and Cuneiform were the worst for the extraction accuracy. Finally, Tesseract, which has been used in all previous work that extracted code from video tutorials, was never the best choice for code extraction for neither video frames nor screencasts. Thank you.